Did Fermat prove this theorem? This is the question that has shaken humanity for the centuries. No, he did not. Fermat claimed to have found a proof of the theorem at an early stage in his career. Much later, he spent time and effort proving the cases n equals 4 and n equals 5. Had he had a proof to his theorem earlier, there would have been no need for him to study specific cases. Fermat may have had one of the following proofs in mind when he wrote his famous comment. Fermat discovered and applied the method of infinite descent, which, in particular, can be used to prove FLT for n equals 4. This method can actually be used to prove a stronger statement than FLT for n equals 4, viz. x4 plus y4 equals z2 has no non-trivial integer solutions. It is possible and even likely that he had an incorrect proof of FLT using this method when he wrote the famous theorem. He had a wrong proof in mind. The following proof, proposed first by Lame, was thought to be correct, until Liouville pointed out the flaw, and by Kummer, which latter became an expert in the field. It is based on the incorrect assumption that prime decomposition is unique in all domains. The incorrect proof goes something like this. We only need to consider prime exponents. This is true. So consider xp plus yp equals zp. Let R be a primitive pth root of unity, complex number. Then the equation is the same as x plus y, x plus y, x plus r2y, x plus r, p minus 1, y, equals zp. Now consider the ring of the form a1 plus a2r plus a3r2 plus a, p minus 1, r, p minus 1, where each I is an integer. Now if this ring is a unique factorization ring, UFR, then it is true that each of the above factors is relatively prime. From this, it can be proven that each factor is a pth power from which FLT follows. This is usually done by considering two cases. The first where p divides none of x, y, z. The second where p divides some of x, y, z. For the first case, if x plus u equals u asterisk operator tp, where u is a unit in z, r, and t is in z, r, it follows that x equals y, mod p. Writing the original equation as xp plus minus z, p equals minus y, p, it follows in a similar fashion that x equals minus z, mod p, plus 2 asterisk operator xp equals xp plus yp equals zp equals minus xp, mod p, which implies 3 asterisk operator xp equals o, mod p, and from there p divides 1 of x or 3, x. But p greater than 3 and p does not divides x, contradiction. The second case is harder. The problem is that the above ring is not in UFR in general. Another argument for the belief that Fermat had no proof, and, furthermore, that he knew that he had no proof, is that the only place he ever mentioned the result was in that marginal comment in Bachet's Diophantus.